Can you hear me?
Yes, we can hear you, Jared.
Okay. Let me know if you can see the screen.
Yes, yes.
Okay. Is my voice audible enough?
Yes, yes, you're audible.
Right. Fine. So welcome to the second session of this 4 days week run up. So yesterday we covered the introduction and maybe just to do a recap of what we did. What we did is we did basic electrical and electronic symbolic representation. We also did, we understood what we call ranks. So I prefer you guys should be taking just, if you have a pen and paper, just take notes, just note something so that you can also refer to the video, and when the course is done, I'll share with you the material. You can go and refer on your own. Yeah. So yesterday we learned about the different symbolic representation of electrical and electronics. We also did how ranks are represented, voltages and ones. We looked at timers, that is T on, delay. We also looked at T off, delay. We looked at relays. The relay are of two types, that they have two contacts, that is normally closed and normally open, and we saw the differences between the normally open and normally closed. And if a sensor say is normally closed, I hope now you understand, if you power a relay or if the sensor relay is powered and it's normally closed, it will definitely normally open. And if it's normally closed, if it's normally open, closed. So some logic interpretation you need to understand. That's what we captured yesterday. And another thing we did, we have around. You can see my screen. This is where we stopped yesterday, and we'll just pick it up. This was our first rung, which we started with. We added this rung, we added a third one, and we added a fourth one. So today we are continuing with the same, just advancing the ranks. So for those who didn't attend yesterday, I'm very sorry about that. But we'll share the material, but at least I've given you what we did yesterday. So today we'll continue with the next session, which will going to look at more understanding more ranks and this switch representation. So these are normal switches. If you look at a lamp, this is a representation of a lamp in electrical symbol. Also, this is a switch in electrical symbol. This is in a drawing format and not in a PLC format. So at some point you'll be able to represent these switches. We now know what this is, the basic programming language for PLC. Industrial wide, it's the starting point of any PLC programmer. So the first thing is understand the ladder logic and how you're able to convert the logics into ladder diagram. So we also know about logic gates, and logic gates are just the AND gate. We also looked at AND gates. We look at the OR gate and its symbolic representation. For those who are not there yesterday, this is how an OR gate looks like. So yesterday we were able to look at the OR and looked at how to write a statement like this one. These are a representation of a logic statement, which you have to convert into an electrical signal, and then from the electrical signal you now convert it into a ladder diagram. So this is the statement, and then if you come here now, you come and write your lines. Yes, you got lines, and then from there you come and represent electrically. And then from the electrical representation, you now go to the ladder PLC logic representation. And this is a rung of our logic. Right, so I think that's quite much of what we did yesterday. Yeah, for the logic, or this is the OR gate, how it looks like. And this is the statement. This is the logic statement. This is the symbolic representation in a digital format. For the AND gate, this is the representation of an AND gate. You use a dot, it's like a multiplication. This is like a D. And then this one is like a D, but it's been swiveled in one side. So like look like something. So this is the symbol. We did yesterday. So to continue to advance our circuit more and more, and just be keen enough, because these are the circuits you're going to get assignments from, tests. You're going to use these 6 statements to develop your PLC logics. They've just come from this concept that we are doing here. If you understand this concept, then definitely from in the PLC programming book, you should be able to actually understand it. Yeah, so let's proceed on. So this is where we are yesterday. We have already had 4 ranks. We say the rank is a complete instruction of a PLC logic. So this is one logic, this is another logic, this is another logic, this is another logic. Yeah, and if you look at the logic here above, which after you read through the book and be able to understand what this so a ground test is just, you know, when you want to test this for an industry, or you have an equipment, your PLC, you should do a ground test to just in case of leaking. If doing a ground test, this is what you mean. You have your transformer here, you have your fuses, your PLC. This is the rung. So we assume this power is going to the PLC to energize the inputs. Okay. So for that matter is, if you have a short circuit on the transformer, the power will flow this way, and because of the higher current flow, the fuse will blow. Now, when the fuse blows, there is current remaining here. So this current will be hanging, but because you ground the system, because you have a ground, the nearest ground point, the current will go into the ground point. The same thing happens here. If there's short circuit within the LED and this switch is off, power will not go this way. It will definitely be grounded at the soonest possible, because you don't want to damage the PLC circuitry. By you do a ground test, and you need, if you're doing wiring for your PC, this is a very sensitive item and very expensive, so you don't want to lose it, because it's the power that it has, it's quite enormous. So let's go to another logic, which we mean by latching or sealing latching contacts. So what we mean by latch, a latch contact is a holding circuit. It's whereby you have a circuit and you want to hold a signal. That's what we mean by latching. Maybe you want to press an on and you want the switch to remain on for some time. That means you're actually latching the circuit. So from the notes, sometimes I may not be able to explain all the notes. I'll just be giving you the lecture, and then for your case, you can do referrals and the notes later when you're done with the course, for you to understand better. But for this lecture, it's just a matter of letting you know. Just be picking some few points here and there, which I decided to do, and then we'll be on the same page. So here we have, if you look at this statement, this is particularly useful for making a momentary push button switch, as if we were a maintained switch. So it's like you're maintaining the switch, but it's internally held within the circuit. You press once and the circuit latches inside the PLC. It's not like you're going to hold a button. You just press once and internally the PLC will be able to latch itself. So that's what we mean by a latching or a sealing contact. So this can be done with momentary push button if we include a relay in the circuit, that is where there's a latch as shown in the ladder diagram segment, 0.13. So first, this is how the logic goes by. First, when power is applied to the rails CR1, if you apply power here, okay, then what it means is, since we are assuming S1 has not yet been pressed, so this S1, this is the switch you're talking about. This provides a path for current to flow. So current is already in this part. This is your load. This is your relay. So this is a relay. We said this is a relay coil from yesterday's lecture. Right? So when you have power in this line, you want power to go to this side, but you want to have some latching circuit, right? So we go to the next statement. This provides a path for current to flow, S1, S2, right? And the coil of CR1, which energizes CR1. So as soon as CR1 energizes, the NO contact in parallel with S1 closes, since the circuit CR1 is operated by. If you press the circuit, if you press the start button, look how the power flows. Power flows from S1, goes to S2, and CR1 is referenced by CR1. Okay, this is the NO of the relay. So we're talking about the relay here. We are taking this relay contact NO, normally open, because you can see here, for a normally closed it's always crossed, but because it's normally open, it opens. And then, since this is on, power will be available here. And this circuit will continue flowing continuously because we powered this one became energized, it is high, and because of this holding circuit, look at the way it is, it's this way. So this circuit is complete and it continue being powered forever. Okay, so this is what we mean by that, and that is a holding. You can do it mechanically. Itself has these logics which you're going to do programming, and you'll understand how they work. But this is the representation of circuit. So this is the stop. This is like an emergency stop. We said an emergency stop is a contact which is normally closed. You see, it's already normally closed, but this one is normally open. So if you release power from this end, this is a latched circuit from here to here. Okay, now that you pressed here, power flew to this side, then took this reference, it came here, it held the circuit. So this circuit is on continuously. If you want to break the circuit, you press this button here, and then power disappears. Yeah. So when power goes off, this one loses power, And because this one is not pressed, this one will lose power and the circuit becomes off. The concept I was explaining here. This is the concept. So I won't be reading much of the lecture notes, just be giving you guided understanding of how the circuit works. Okay. So I'll go with my next statement. Many machines used in manufacturing are designed to go through a repeated fixed cycle. An example is this is a metal cutter that slices sheets of metal when actuated by an operator. By code, all cycles have an actuation, an anti-repeat and anti-die feature. Each of these is explained below. So what do we mean by that? This means that the machine can only be cycled by an operator pressing two switches simultaneously that are separated by a distance, such that both switches cannot be pressed by one hand. This assures that both of the operator's hands will be on the switches and not in the machine when it is cycling. This is simply two palm switches in series operating a run relay. So the reason for this is because of a safety thing, because if you're looking at a big, huge, and the accident may be fatal. So that's why they need you to be most concentrated on, concentrate a lot when you're doing making such kind of decisions. So you don't make a mistake. Because if you press once and the machine starts cutting, definitely it might run you over. So that's why they want you to be attentive. Even if you press one switch by accident, the machine will not start running. So that's what they mean by that. So this is what I was just explaining. You have to press this for the shredding machine to start acting. Right? So I go to the next statement. So since both switches must be pressed within a time window, we will need a time relay for this feature, specifically a delay on or T-on relay. Notice that we have taken the 200 key that we installed and added an additional circuitry to perform the anti-tie down feature. So this is what I mean by that. So we have added a T-on. Why do we mean that by that? We have a timer here. We explained yesterday what a TDR is and what a T-on is, right? So this is a coil. Anytime you see a CR is a coil, an S is a switch, a PB is a push button, a T-on is a T-on delay timer. So how it works is you press this button, okay, switch one, and we said yesterday, since these are two switch contacts, the switches are the same. They are two contact switches. When you press switch, it has two contacts. So one goes here, one goes here. And one other goes here, another goes this first switch, second switch. So you have, you press this button with left hand, press on the right hand. Now power starts flowing from this circuit here. Now this CR1 is not yet it closes. What happens when CR1 closes? This one is energized. Okay. So when this one is energized, TR1 is here. This is a timer. Talked about TR1, 0.5 seconds. So this one has not yet completed the cycle. So you have timer here, this is running, and you have its coil here. This is a coil timer. So this timer is on, but it has not yet completed the cycle. If it completes the cycle, it becomes energized, and its out When it completes the cycle, it will output will open. Okay, so when the output opens here, now this one completes the cycle. So this one now becomes on, and this one now disappears. Okay, and so you have this switch here, switch 1, waiting for a press. So that means when you press this switch, it will automatically activate the timer the second time after the timer has elapsed. Remember, there are two scenarios here. You have a timer and you have simultaneous operation. So, but if you press switch 1 and switch 2, as long as the timer is done, you will get an output here. And in this upper rank, so this is first rank, okay? So you press this, you get this first rank on, but before the timer elapses, this becomes on. This is what supplies the power. But before this timer is done, there's no power. So if this timer is already out, if you press this switch, because there's no circuit completion here, nothing will work. All right. So that means the first turn, because you want 200 operation, it's a 200 operation with anti-tie down and anti-repeat. So you cannot repeat the cycle. You first has to complete the first cycle on the first run. Then if you want to do another cycle, you have to complete the second run, of which the timer has already counted down. That's when you'll do the second cycle. So that's pretty much about it. So these things you'll do them in your PLC programming. You'll actually when you simulate them on the PLC program software, and you see what happens. It will be real time, and you'll be able to understand, as long as you have the notes and you're taking notes at this time and just understanding what's happening. So surprises and possible injury for the operator, if the machine should eventually go through a second cycle. Therefore, circuitry is usually needed to assure that once the machine has completed cycle 1, it stops and waits for the run switches to be released and then pressed again. So that's what I said. For big machines where you have industrial applications that are quite heavy and it's dangerous for the human being, maybe you're dealing with a boiler furnace, to have a coordinated approach. You don't want to injure anyone because things can happen. If you're doing a boiler or you're doing a shredding machine, which is grinding stones and stuff, if maybe the blade misses the target and you are there, so we want to prevent such kind of injuries in factories, because you don't know what happens in the factory. Power can go out anytime, things may happen. Yeah. So these are some of the logics you are trying to understand as you build across these anti-circuits. You need to know how to develop them. This is an anti-circuit logic. Yeah. So this one I'll give you an assignment maybe when you guys are ready for, when you're already ready for, and I tell you to do an anti-circuit and you program it in the PLC. And how are you able to, you're just given a statement and you're told do this task. The timer has to what the next one done. So those are some of the questions you're being asked in a PLC programming scenario. No one gives you direct approach. You have to create a logic in your head and come up with a solution and see how you're going to implement it. Yeah. So that's just about it on that anti-reverse circuit. right? So we have another logic here. Okay, we have another logic here. Same logic. Okay. So this is 1.34. So 1.34 is another rung, and let's see how it works. Okay. Is shown in figure. This is what I'm reading here. Single side phone figure 134. Note that we will be using both NO and NC contacts. So most of these terms NO, NC are very common in PLCs. AND gates, OR gates, they are very common. You can't miss those ones. A momentary push button, switches, a logical representation of them. These are common words for PLC programming. You can't escape those ones. It's just about logics and you understanding when are they applicable. That's it. It's nothing hard. It's nothing to be worried about. It's something that is easily manageable. Yeah, so we can say also know that for the time being, the start switch 1 is shown as a single push button switch. Later we will add second-handed tie down and anti-repeat circuit diagram. So this is what we're talking about. Okay, so here, look at the rung. We have our switch, and then we have our cycles. Okay, so these are like cycle locks. So let's see how the circuit works. Let me give you just a brief explanation. You press this one. You press this one. Look how we are going to analyze this circuit. You have a switch. You have a run. This is like a coil. CR is like a coil. It can be a relay, but an internal relay of the PLC or an external relay of mechanical relay. But here we are dealing because we want to develop this circuit from an external mechanical relay to a PLC logic and its own complete circuit. So pressing this button and CR1 is on, right? So when you press CR1 becomes on, but it cannot yet start running. Now, we need CR3 to come on for the run latch to engage. So we need to trace CR3. So CR3 is somewhere here, but CR3 is dependent on this cycle, right? This contact. So when you press this one and this cycle 1 energizes, now CR3 closes here, power flows here. Okay, but CR1, take note, CR1 is here and CR1 is here. So when CR1 engages, it becomes on, this one goes off, takes out, but immediately CR1, as you press immediately, you press this one, it turns on instantaneously. Okay, you press CR1, you press start, turns on CR1. There is a circuit before it goes off, the power goes on, and CR3 coil holds this circuit lock. Okay, so this is just a brief explanation. Let's go to what we mean by that. So just read through these statements. And that's why it's important for you to first I explain it so that you understand, what we mean by these statements below, and then from there now you can be able to make your own summary. Okay, so let me just put the pointer. So when the rails are energized, we'll assume that the machine is mechanically positioned so that the cam switch is sitting in the cam detent. That is the normally contact LSA1 is open. Our cam circuit. This is the cam. Okay. So this is the cam. When the cam rotates, this is going this way. As the cam rotates, it's pulling this thing this way. And then this lever goes out, and then this one comes in. Right. So we have the NO, NC, and NO. So you make a pivot. So this is a cam that is rotating. So it rotates. At some point it will come and touch this side, and then as it still rotates, it may not. So when it's on this end, if this roller is on this other side, there will be no contact here. But when it gets to this point, there's a contact between the common and the normally closed. So that's what we mean by that. So we go again to the energize. We assume the machine is mechanically positioned so that the cam is sitting in the cam detent. That is, NO contact is open. At this point, CR1 in the first rung will be off because the start switch has not yet been pressed. So CR2 in the second rung is off because CR1 is off. So look at what we are saying. CR1 in the first rung will be off because the start switch has not yet been pressed. So this is still off because you haven't pressed this one. Now, CR2 in the second rung is off because CR1 is off and LS1 is open. Yeah. So CR2 is off because this is open and these one are open. Now, next statement. And CR3 in the third rung is on because LSB1 is closed and NCR1 contact is closed. So because this one is closed, that is cycle lock. Okay. Now, as soon as CR3 energizes, the CRNO contact in the third rung closes. So as soon as this energizes, this one closes and will hold the circuit. Okay, so this one, it will hold this circuit. So here at this point the circuit is powered and the machine is stopped but ready to cycle. Okay, now so we press the start switch S1. As we press S1, CR1 becomes on, and then in the second rung this CR1, this one, you have this one on. Okay, CR1 is on. Since the NO, look at the CR3 here. Okay, it's already closed because CR3 is on. So we have already have CR3 is on, and we pick this reference, we pick it here. Because you press this one energizes, this one energizes, the run latch starts. Okay. Next one, this applies power to the machine and causes the cycle to begin. So the cycle start is here. So the cycle run is now beginning here. Okay. Yeah. So as soon as the cam switch rise out of the CAM detect, LS1 closes and LSB opens. When this happens, LS1 in the second rung, cells CR on, the coil 2 is somewhere here, second rung. As soon as the cycle done, so this one is a cycle, okay? And how this cycle arrived at? It's alive because we have the cams, which we talked at this. So this is the cam rotating. In the first cycle, it will connect NC and common. In the second cycle, it will connect common, NO and common. So that's what you mean by a cycle. So it runs one cycle, disconnects another cycle, connects again. And then we have relay, we have contacts here, which you're getting now the signal from the PLC. So those NO and NC are these ones. These LS1 and LS2, these are the contacts we're talking about. Okay. So we go to the next statement. I'm just trying to be a bit slow so that you grasp as you go along, so that no one is getting is slow at any given point. But if you feel you need to get some clarity, please ask. Because I know that's why I'm taking it a bit slow, and I decided to use these self-explanatory notes so that you can also be able to understand if you don't really if you want for your revision. It does release the start switch before the machine finishes its cycle. CR1 will de-energize. However, in the second rung, it has no immediate effect because the contact CR1 and CR3 are sealed by this. This is the first cycle from the CAM. Also in the third rung, it has no immediate effect because LSB is open, which disables the entire rung. So LSB, these are the rungs, and these are the ones we're talking about. These are the rung cycles. So now, if you now understand how so you first, it's like, let me take the wheels here. Let me just pick something. I want to tell you how to analyze this circuit. So this is the CAM, okay, and I have common, I have NC, and I have NO. Okay, now this is the point where we have this one connected here, and there's a connection between this one and this one. So look at what I mean by that. So this is the CAM I'm talking about. So now you have this rung is running, which is represented by just a minute. No, that's not the correction one. Maybe do cancel. Go to the next one. Yeah, this one was supposed to use this one. So I do a new one. This one, and I draw my wheel here, and I say this is the rung. This is contact 1, contact 2, contact 3. This is NC. This is NC. This is, sorry, what happened here? Let me just try and wrap this. So I think that is okay. I think so that's how the circuit works. And now let's try and look at the next step. The combined circuit, that's figure 3.5. So 135 shows a single cycle circuit with start switch replaced by the two ranks are to perform the second handed and tie down and anti-repeat function. So we've combined this circuit. So combine the two circuits. Remember, we have the anti-tie down and the circuit second handed and anti-tie down. So you've combined the circuits. And now you have four ranks. The first rank. Okay. And now we now this is now what we'll go and do in your PLC simulation, and you'll be able to understand more what this means. That's to logic. Okay. That let me give you a simple logic. Say, let me give you a simple logic. What do you mean by that? I'm giving you a simple logic. How we're going to analyze this circuit. So we have S1, S2, which are connected. So we can write the circuit logic as this. S1 must be connected together, must be ANDed CR1. So we'll say CR1 is equals to S1 dot S2. This is a multiplication. We AND this one, and we are ANDing. And then we AND the input. We again AND. We AND. We AND. We AND this one. Okay. But inside it, we are going to OR TDR TDR1, which is inverted. You can put a negative sign to mean it's inverted, or CR1. Okay, plus you OR. The OR symbolic for this one is an OR. CR1. Then you close your bracket. So that means this is okay. So you have first rank. Now S1 dot this blah 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 is equals to CR1, which is this one. And now you can go now to the second logic, write the same thing, because this will be a starting point from maybe you're given a statement or a function and you're told to develop a circuit for it. You'll first write this presentation here, even before going to the logical diagrammic representation, so that you can do it in your head and understand this is what I want to achieve. Because for you to be able to get to the ladder programming, you must be able to write this statement correctly. This is what you're going to put in the PLC. And if you write it wrongly, then the PLC will give you whatever that you actually produced. So they always say garbage in, garbage out. if you are able to figure out how this circuit is represented, then that will be very good for you. On the right track, and if you do practice a lot, you will be fine. Okay. So now for you is be able to, maybe for you can also be able to understand for your own assessment, maybe these are some of the things I'll be picking up, and see if you guys are getting to understand what a PLC means. You just write a logical representation of this and try and see if you can come up with a logical statement or a pseudocode for it. Okay. So, and that's it for that kind of logic. This is some of the safety circuits that you can meet in the industry. That's just an example, but they are quite a lot. This is just for you to be able to understand. But into logical representation, maybe that I mean later. When now will now to see if you're ready for, you're ready now to get into the hardware and be able to program it. Because for you to be able to program the hardware, you must pass the simulation test. And because you don't want to play around the PLC, because the PLC is, you just need to put what is really there. When you've already done your simulation and you know everything is okay. So some of the machine control terminologies, we have an on, off, run, stop, jog, inch, and cycle. Okay. So let me give you, let me try and see if I can come up with something, what that means in a PLC world. So, just a minute. Of course, an on is just the machine is on, does not mean it's running. Then off means it's just powered. Running, it means it's now in active state. Stop means it was running, but now it has been put to stop. When a machine is told it's in jogging mode, the machine is just being pulsed to come on or off. It's like it's being told, you wait kidogo, just wait a little bit as I engage. Wait a little bit as I engage. Right. And then inch is the same as jog. Some of the things you meet later in protocols. This kind of training. Those are very easy steps that you'll meet. So I'm going to give you, like, I hope you're going to see this. This is like a PLC, okay? So this is a typical PLC. I hope I can see. Chris.
Yes, yes. Jared.
So you can see the image, eh?
Yeah, we can see the image.
Yeah, so let me just try and do something. So what do you mean by that? These are the LED indicator status. So this is like a real-time PLC, field PLC, very powerful. We have the run and stop. This is an LED for run and stop. This is for error. And then this one is for status. Okay, and then you have these are the output inputs, and then these are the outputs. So these are the machine status, PLC status. And here you have your power connector. You put in your power movable user wiring cabinets. And for programming, this is a Ethernet connector here. Put it here, and then you have your wires in here. Okay, this one you'll be able to see them as we program with the course, and you'll be able to understand those kinds of. You'll be able to understand even what you mean by this cycle time, memory load, workload. But that's for advanced PLCs. When you now go into real PLC and advanced. But basically, this is how a PLC is. I just picked one PLC from Siemens, and you see how it looks like. You can do it modular. You can add more logics to it. You'll be able to communicate. So you see, you have modular. You have modules here. Yeah. I'm just trying to show you how a PLC look like. The LED. So back to business. I was trying to learn, and they are here explained very well. So a state in which machine is cycling or performing the task is in run mode, right? And that's it. Of course, hand operation, most PLCs to hand operation, a control design method in which a machine will run or cycle unless two separate push buttons simultaneously pressed. This is used on machines where it is dangerous to hand feed the machine while it is cycling. The two buttons are positioned apart so that they both cannot be pressed by one arm. So you can see this is what you mean by that. This is a safety mechanism in a very dangerous machine environment. So the summary, although this chapter gives the reader a basic understanding of conventional machine control, it is not intended to be a complete. You can always engage. With an understanding of basic machine controls is the foundation needed to learn the programming language of programmable logic controllers. As we will see in this subsequent, programming language of PLC is a graphical language that looks very much like a machine control electrical diagram. So these are review questions which I think you'll be able to, I'll assign you guys some point in time, and you guys will submit them, and we see if guys are able to answer these questions correctly. Of course, this after you've been shared with the notes and you've given time to understand. So now, is there any question up to that point? Because now we want to go into the programmable logic controller. That was basic introduction to just some circuitry designs and representations. If there are no questions, maybe we can reserve them for the last part, just 10 minutes, and then we can be able to answer. So chapter 2 is programming the programmable logic controller, PLC. The history, whatever, the scan time, okay? So these are the objectives of the course. And once you have these ones, you're now set for the, it will give you a guide on what we're going to do. So let me begin. I won't to go into much of the theory, but this will be for your own reading. So I'll just pick some key points to note. So a physical description of various configuration of programmable logic controllers, the functions associated with the different components will follow. The chapter will end logic obtains input. This because yes, there are a lot of changes during the design process due to complexity of user requirements. So they had to change logics here and there. You can imagine how the old PLCs were. You had a lot of wires connecting. Imagine you have wired physical wires and relays doing the work. It was really not easy. You have like 1,000 relays, and each relay you're powering and you're doing the logic. Actually, that's how the switching was done. Because this is on here. So you had to have like a number of 1,000 relays. You wire them hardwired, you solder them, you connect. Problem situation because they had a lot of with one wire which is maybe can NO you short circuit, big circuit, and if it go 400 it go without 10 fees. And so the relay don't report this should have so sometimes they like it's not there. So, and it's a new industry page. So just giving a brief history, we had the single board PLCs or open frame PLCs, and then we had the closed frame PLCs. Single board were maybe just like the microcontrollers. Yeah, and the others were like the real PLCs. So these were the single board. It just looks like an Arduino, but it's not. It actually looks like an Arduino because just one single board. Yeah. And then we went to the next version where we had Shubo. So at least one was a bit closed. And then now we go to the modular, which are now the current PLCs. These ones are modular. So this is the Omron PLC. This is a very industrial, heavy duty. And then if you go to the one I was sharing with you, this one. So I was sharing with you. This one is also modular, but this one from a different manufacturer. See, it's modular because of this. This is the modularity. You have the first module, you have the main PLC, another module, you can have 10 modules. That's what we call modularity. So most now the new PLCs, the current age PLC, are modular. They are not fixed, same as this one. This from a different manufacturer. The other one was Siemens modular. So you can add extra inputs and outputs as you require. Okay. So you can Arduino, where you have Arduino Mega has pins which you're going to hit around 10 or 20. Then the rest of the pins are very useless. So the reason why PLCs are made to be modular is because for you to be able to save on costs, you don't want to incur so much cost on buying a very big PLC that has, I don't know, 20 analog inputs and you just need 2. That's a waste of money and resources. So other PLCs are very modular, and that is the beauty of these controllers. You can expand as a need to buy, and the power is still the same. The cycling time is still the same. So I'm just giving you briefs. Then you go to the processor. These are the same as CPU, and it's very fast. We are talking of nanoseconds. This is the speed of a PLC. The PLC works in nanoseconds. I think we are talking, if you look at your computer is fast, but it's not as fast as a PLC. The PLC is able to interact with 1,000 inputs within a fraction of a second and be able to give an output within the next minute, the next second. So it's really, really, really powerful, and the speed is nanoseconds, around 10 nanoseconds. That's the highest speed I think I've interacted with. 10 nanoseconds, highest PLC speed. It's a lot of speed. You can't even. Talking of seconds, and yet you're talking of a second. So how many nanoseconds are there in? If you do the multiplication, you understand any sensors. So yeah, something to me. So that's why they are very powerful, and that's why they have been in aerospace engineering, in manufacturing, where we need high-speed processing power and capability. You can never find machines in your PCs or whatever the desktop industry is, because they are very for the machines. The sensors are something that things that commit. So that's then you have the input and outputs. These are just basically talking about the modular. When you add the modules, the thing about modularity, that's what you mean by that. Then because you have a power supply, this is the main power supply. So the current PLCs have an external power supply, which is also modular. So that when the power supply is the one that fails, C is still intact. Your phone is so intact. It has the battery, the power, the screen. If the screen goes off, but the PLC is made industrial in a way that if the power supply fails, it only fails on its own, totally isolated from the PLC. If one of the input module fails, it fails alone. The PLC, the main processor, the main brain is still intact. You just replace the module and life goes on. And it's called hot swapping. Hot swapping is a technology where you replace a module and the PLC is still performing functions. So if the module is the only one that is broken, the PLC will continue running other processes, and you hot swap. You just plug the pins and insert the PLC. It picks the addresses and continue running the other operations. You not even realize how it happened. But that's how hot swapping is done. For industry PLCs, because you cannot stop a full factory from running, you want to change a module. So they are made industry in a way that the same way you can plug a mouse and plug it back, or you plug in a flash disk and plug it, that's hot swapping. So even for the modular PLCs, you plug in a module and plug out, you won't realize the difference. And your sensors will still be, you won't affect the production on your end. So that's what we mean by that. And then we go to, of course, the programming unit. This is like the software. This is the software where you use for your programming, where you feed the program into the PLC, you write your logic into and transform it into a program block, and you use it. So this is what we meant. This is a PLC programming cable. This is maybe the interlink. These were the first controllers. Yeah, currently we have serious programming. This is serious PLCs. You don't need those things. You just need an Ethernet cable and you're able to plug into the PLC because they are very advanced, like I had shown you in the previous diagram. So this one. So you have just need a cable here, an Ethernet cable, you plug it in and you take it to your PLC and there you go. You don't need this interface. This one. This is outdated. This is outdated technology. This one. Now it's current technology. We are talking about the millennials here, the age of technology. So this is just a logic block diagram. So if I tell you maybe draw for me a logical presentation block diagram of a PLC, this is what I expect for you to do. If you get this question, you need to know the discrete inputs, analog input, and the registers. Then you need them. PLCs have a ROM, they have a RAM, they have a flash memory, they have EEPROM, and SRAM. It's the same way like a computer. A PLC is just a mini super fast computer. But of course it can be able to interact with the environment with ease because you connect directly sensors to it, as opposed to your PC. Then the output, we have a discrete, analog, yeah, and we have digital displays. Yeah, those LEDs. What I was telling you, so these are some of the things I was meaning. So you have your inputs here, whether they're going to be analog or outputs. Then you have your outputs here, whether they are relays, transistors, or analog outs. Then you have your LED indicators here. You see even here they've written for you DQ. DQ means digital out. D in means digital in. Then this is the CPU number. And then if you open this bracket, you'll find those things there. Okay. So that's what we mean by that. And let me show you something. Okay. So scrolling down something. So like here, so for instance here, I'm just showing an example of PLC. So see, like this may be a programming a PLC, and you see this is digital input 1, digital input 2, blah blah blah, digital input 0, 1, 1, 1, all through. This is for advanced programming. This is why we interact with such kind of systems. and then go to your network layout. Yeah, you see how the network is. Okay, so you see how you're doing it. So you have your input here, you take it here. This one you just reference it directly. Take another one, reference it here. Here you reference it here. Here you reference it here. And that's how life becomes so easy. Okay. So these are some of the things we'll be doing when you'll be doing now the actual programming. And you like it, you love it. You love just interacting with the PLC, the simulator, and everything. So that's the logic block diagram. So how it works. That is a simple working logic of a PLC. When power is applied to the programmable logic controller, the PLC operation consists of two steps. One, so if I tell you, maybe explain to me how a PLC works on startup, what happens? Okay. When power is applied to the programming logic control, the PLC operation consists of two steps. One, it updates the inputs and outputs. It checks for the inputs and output states and then updates. Then step two, it solves the logic ladder. All right. So what does that mean? This may seem like a very simplistic approach to do something that has to be more complicated, but there truly are only these two steps. If the two steps are thoroughly understood, writing a modifying program and getting the most from the device is much easier to accomplish. With this understanding, the things that can be undertaken are then up to the imagination of the programmer. You will notice that the update to solve the ladder sequence begin after startup. The actual startup sequence includes some operations transparent to the user or programmer that occur before an actual PLC on the user program begins. During this startup, there may be extensive diagnostic checks performed by the processor on things like memory, input devices, communication with other devices, if they are present, and program integrity. In sophisticated modular systems, the processor is able to identify various module types, their location in the system, and addresses. This type of system analysis and testing generally occurs during the startup before actual program execution. All right. So this is what happens. If you power up a PLC, you just see the PLC blinking some LEDs, the status and LEDs will tell you if there's an error, if it's running, so it will tell you first it's powered on, then the LED changes status. If there's an error, it will give you a red error, and then you'll be able to go to the program and see what the error is. If it's a module error, it will indicate a reading to start flashing, telling you that maybe the error in the module is an error. So that's what I mean by the startup period. So it does a startup, then from the startup period goes to checks the inputs and outputs. Then on the third cycle, the third step, it updates the logic diagram. Then on the next scan, it now updates the registers. Registers are memory locations in the PLC. So these are what we write to, we address them. So that's what happens in the PLC when the PLC is now working. So you need to understand these things so that you know how the PLC works. It's not like it's just the same way like a phone. You power it on, it checks itself. The same way like a vehicle, you put the ignition on, the engine status LEDs are, if there is low oil, low coolant, low nothing, there is low fuel, it will start indicating. If maybe the passenger has not tied up the belt, the passenger signal will light. This is for a vehicle system. So the same thing happens to a PLC because it's a like PC. So it self-checks itself, self-analyzes, and knows what's happening within its environment. Okay. So of course you see that it will check every input. If you have 500 inputs, it will check all the inputs before it makes any decision. Then when it's checked, it updates the register, then goes to the ladder program. It now runs the ladder program in a cyclic manner. Then if a function is needed to be executed, it now executes the function of the first cycle. And then again reads the inputs on the second cycle, then updates the program function, then goes to the third cycle again, read the inputs, update. This is some of any PLC class: scan cycle, scan time. So those are some to interact with when you're doing PLC, and you'll understand. Okay. So solve the ladder. So after the IO has been accomplished, it has checked all the input and outputs, the analog, digital, whatever is. PLC begins executing the commands. This command typically referred to as the ladder diagram, and the ladder steps using relay contacts and coils. The ladder is drawn with contacts to the left side of the sheet and coils over the time control system or relay based. Step was used for electrical schematic of those systems. This is the guys who were the first ones to make a program. They use the relays, and up to date engineers maintain the relay logic concept. The relays, and they normally open, normally closed, because that's those are the main building blocks. So this is a typical PLC program, pure PLC program. Now this is now a full PLC now in action. Okay, so you have your circuit here and you understand what this means. Yeah, it's normally closed, normally open, normally closed. So you can see all these combinations. There can be a lot of matrix. You need to have Boolean logic. Maybe if you have Boolean logics here, maybe you have those logic circuits, so you want to do some computation of which the AND gate, the OR gate. This is now where it comes very useful, because if you have 100 inputs and you don't know what will happen, you have to analyze them slowly by slowly and then see how you're going to implement them in the PLC. Yeah. So the symbols used in figure 2.6 may be foreign at this point. Okay, yeah, so I know these are quite strange, but you learn them as we go by. So what we meant by the rank, this is the first rank, second rank, third rank, fourth rank. And the signal are on the left. The coils, those are the outputs, are on the right. That's how PLC programming is done. Because you first supply power on this line, and then you get power on this line. It's transmitted to this line, and these are the expected outputs. Yeah. So the symbol used may be foreign at this point. The symbol at the right side of the right, the board CR1. These are just software coils of the relays. Okay, these are software coils. And the symbol at the left, which look like capacitors with diagonal lines through them, are the contacts associated with the coils. So the symbols that look like capacitor without the diagonal lines through them are normally closed, normally open contacts, and those that are analogous to which a switch is normally off. When a switch is turned on, the contact closes. The contact symbols at the left side look like the capacitors with diagonal lines through them are normally closed contacts. And a normally closed contact is equivalent to a switch that is normally turned on. It will turn off when the switch is actuated. So you need to understand this concept. Normally closed, normally open, normally closed. Those are things you'll be interacting with. But those are logical logic that you'll be writing in your head, and as you analyze the circuit and the logic required for you to implement a function. Yeah. So of course, this is just a theory, a bit of theory, but just pick this point that you can note. One rule is different from general electrical operation is the direction of current flowing in the rung. In a ladder logic, rung current can only flow from left to right and up and down, and not from right to left. That is the rule of ladder logic. Power can never come from this side to this side. It is from left to right. And that is the rule. So when you're doing your circuit analysis, you need to understand. Yeah, like this circuit looks quite complicated, yes. Yeah. But of course, this CR1 can energize when this one closes, or when this one closes and this one closes, and power goes this way. Or when this one closes, this one closes, this one closes, and power goes this way. Or when this one closes, this one closes, this one closes, this one closes, this one closes. Or when this one closes, this one closes, this one closes, this one closes, this one closes. You see how the power goes? So you can have like a combination of 5. You have the first combination is this one, number 1. Then go to number 2, this road. How power will go again? Number 3, this route. Number 4, this route. Number 5, this route. All those are possible combinations. Okay, so it's up to you to understand. And these are basically, you can find these are sensors or sensors in the field, contacts, relay contacts. And if you don't capture all those combinations within your logical representation or when you're writing a program, you may not know that a sensor will actuate another process. And you will not know. So sometimes that's when you need to do a lot of simulation, you understand. And once you understand all the simulations, yes, you see, like I was saying, 5 combinations. And you need to actually have that kind of logical approach. Just be free and understand the circuit. Don't think too much. Just check on the circuit. What happens this first route, second route, third route, whatever. Life is easy. So you notice as the current flow in the circuit in each listed above is from left to right and up and down. CR1 will not energize. So CR1 will not energize in the listed below. Okay. So these are the cases that CR1 is not energized. But of course, I've already given you when it can be energized. What I did the summary before. Okay. So to review after the IO, the PLC, this one. To review after the IO update, the PLC moves to the first rung of the ladder logic. It solves the contact configuration to determine if the coil is to be energized or de-energized. Then energizes or de-energizes the coil. After this is accomplished, move to the left side of the rung, next rung, and repeat the procedure. It continues until all the rungs have been run. Whether you have 1,000 rungs, it will do the 1,000 rungs within 10 nanoseconds, but depends on the loading of your program. If your program is too heavy, it can even take 1 second for the PLC to be able to update. If you have 400 inputs, then the PLC will have a hard time. Maybe take like 1 or 2 minutes, 1 or 2 seconds, or even 5 seconds to be able to interpret all the signals together and be able to actuate all the controls. But remember, PLCs are very fast. We're talking of 10 nanoseconds. That is a very high speed. So even if you have 400 inputs, it will be able maybe to capture within 1 second. It's able to capture all the, maybe in the next second, it's able to give a control. Yeah. So sometimes the PLCs are made to be very fast for them to be able to capture all these. So it checks this, it updates the IO into register image, then scans, updates, gives the output commands, takes in again, read the register map, solves the ladder. This is cyclic. So this is a scan cycle. See, this is cyclic. This is how the PLC reads, analyzes the input. It cycles. So PLC's speed is determined by the scan cycle. The scan cycle is update of the inputs and outputs and solving of the ladder logic. This is how you can define a scan cycle. Okay, so you can see the period between the IO and IO update and the next is referred to as a scan. It's a successive IO update before the next actuation is done. That's a scan. Then you can do a scan time. How much time does it take? Right? So I'll give you a simple scenario. So the amount of time it takes the PLC to get from the one input output update to the next is referred to as scan time. Scan time is typically measured in milliseconds and refers to the speed of the CPU and the length of the ladder diagram that has to be solved. The slower the processor, the longer the ladder diagram, the longer the scan time of the system. The speed at which the PLC scans memory is referred to the scan rate. Scan rates units are usually listed in millisecond per kilobyte of memory being utilized for the program. As an example, if a particular PLC has a rated scan rate of 8 milliseconds per kilobyte and the program occupies 6 kilobytes of memory, it will take the PLC 48 milliseconds to complete one scan of the program. So remember, the PLC analyzes a program depending on the program size. The same way, if I'm doing an Arduino program, it has a memory. Okay. So I don't know if I have any Arduino programs so that you can see what I'm talking about. Let me try and see if I can launch something on Arduino. So, there you can understand what a scan means and how the PLC computes for the scan. So, I've given you that example, and as we summarize, before I think this Arduino is loading. Let's wait for it to load. So before a study of PLC programming, it is important to gain a fundamental understanding of various types of PLCs available, the advantages and disadvantages of each, and the way in which a PLC executes its program. The open frame, the shoebox, and the modular PC are each best suited to specific types of application based on environmental condition, number of inputs and outputs, use of expansion, and the method of entering and monitoring the program. Additionally, a program requires a prior knowledge of the manner in which a PLC will receive information, execute a program, and send out information. With this information, we are now prepared to begin study of PLC programming techniques. So now that I've given you, I've told you how a PLC works, what do you mean by a scan cycle, what do you mean by a program logic, what do you mean by input, what do you mean the update period, the startup period, the loading period, the run time. So those are some of the things that I've discussed today. And now you understand when a PLC is in on mode, run mode, jog mode, off mode, what does it mean? When the PLC is doing a scan, what is it really doing? When it's doing an IO update, what is it really doing? When it's solving the ladder, what happens then? How much time does it take for the PLC to do a scan and be able to execute the ladder? Okay, so let me just try and compile this Arduino program. It's a very simple program. Let me just try and open a bigger program from sketches. Just want to use communication because communication are always heavy. Display, let me check something else like let me check something here like this one. Sensors, switch case, let me see. So all the PLC programs are always indicated. What's up, man? So you can be able to compile board. Yeah, so I just wanted to show you how you can be able to check. Let me get the board. Uno. Okay. Okay. So I just compile. You can see so you can see the memory bytes. Sketches use 1.6 bytes, 5% of the program, and the maximum is 32 kilobytes. So this is bytes divided by 1,000, you get 32 kilobytes. So if you look at this example, but of course PLCs, they are very complex programs. So maybe you can get it maybe around 20,000 kilobytes, which is maybe like 20 kilobytes. For factories, you can even go up to MBs. Bigger factory. So for this case, if you want to now to know, you'll take this 1.9 kilobytes. Maybe that's the program size. Now you want to get the scan cycle. You take this one, yeah. Like for example, is Arduino, take 1.9 kilobytes, do the computation here. If 8 milliseconds per kilobyte, what about 1.9 kilobytes? You find how much time the PLC will be able to analyze that program. And that will be the next scan cycle. So that's just an example of how the PLC programs have sizes. So, and it tells you, it analyzes for you how much memory you've used, the capacity, what's remaining in the memory, so that you cannot be able to, the PLC cannot be full. So these are some of the questions I'll need you to answer maybe in the next time, maybe after when we begin now the programming. So just shoebox PLC lists 4 types IO modules, lists 5 devices that will be used. These are some of the guiding questions I'll give in to you. That you'll be able to understand what we mean by that. Right. So at this juncture, tomorrow we're going now to start the fundamentals of PLC programming. Upon the completion, we'll be able to how to convert a simple electrical ladder to a PLC program, the difference between physical components as program components, why using a PLC saves on a number of physical components, how to construct agreement and majority circuits, how to construct special purpose logic in a PLC such as the oscillator, gate, silent contact, and whatever. So that will be covering our next chapter topic, which will be chapter topic. So for today, yesterday we covered chapter 1. Today we've covered chapter 2. Tomorrow we hope if we go with the same speed, we'll be able to cover chapter 3. But if the course is too intense, you just let me know, and so that I can be able to understand from where. But if everything is okay, then we continue the same pace. Then I'll welcome your comments at the end of every lecture. So I won't go into chapter 3. We'll start chapter 3 tomorrow. Hopefully, if you're able to complete chapter 3, then maybe the fourth session we do and then I prepare you for the practicals and the tests. Some of the logic for you to prepare, you go and read and start preparing on how you're going to now start doing the programming logic. I'll tell you the softwares you need to download for you to start up and start doing the tests on your own and do the simulation. And then so that we can prepare when now we can have a real simulation guiding. So with that point, I think I've already kept my time. We have now 12 minutes remaining. So this is a question and answer session. So for those that have questions and answers, these questions or any comments, you can be able to air out now, and then we can be able to answer them. And then for tomorrow, we prepare for the next chapter. Thank you for your time, and welcome any comments and any questions thereof. Are we available? Yes. Dennis, Errol, Emmanuel, Leila, Mary Ahuna, Peter Kihumba, Prince Daniel. Oh God.
Jared, we can hear you from. Yeah, we can hear you. We've been following the session.
Yeah.
And there's one question on the chat from
Okay.
IEEE Kenya. Hello.
So thank PLC, we've talked about the modular PLCs. And what we mean by modular PLCs, have modules that are digital, as a digital out, digital, and any others go in, digital out transistor types. Then you have the analog side. The analog side, you have 0 to 10 volts inputs. Other modules are 0 to 20 milliamps. Others are 4 to 20 milliamps. Others are 0 to 5 volts. So those are some of the combinations you can have. depending on the application and the sensors that you use, a module that is 0, so that you can accommodate your sensor. But if I told you you have a module that is maybe is a module that is 0 to 10, is 0 to 20 milliamps, you can use a converter, and if maybe getting a module is be very expensive. $20 milliamps or 0 to 5 volts. This is DC. Okay. This is DC type. And then, is there any software you need supposed to before tomorrow? For the software yet, maybe for the software I'll guide you is I'll guide you on the software tomorrow, but tomorrow we'll just be doing this logic representation. Yeah, you'll be able to understand these kind of inputs, and then from there you can now be able to go to I'll let you know the software you need to install tomorrow, and then maybe on Thursday, on Sunday, we can be able to do some few programming here and there, and then from there I can share the notes. You guys can go and read, and then from there you can now be able to employ the techniques you've learned from the one. You go and do your own practice. Yeah, so for the software I'll be able to give you tomorrow what you need to get hands-on. Yeah, but also tomorrow we'll just continue with the practicals. So any other queries?
I have one question on power supplies. So for PLCs, on a panel, we normally have like a power supply for the sensors that let's say valves that are controlled by the PLC. Is it the same power supply that is used also for the PLC, or it's different? Hey, is the meeting still ongoing? Am I Misha? Hello, is there anyone on the call?
Baki wawili
I
hapa.
think we
Jared has left.
oh, okay, sawa. Sawa, wacha to end meeting basi. I think we can now end the meeting because I think I don't know if Jared is still there.
Yes, Beryl. Can you hear me?
Yes, I can hear you. Yes.
Yeah, I
So
lost and I was just, you heard my remarks, the last remarks about having the
no,
replies.
oh no, I didn't.
Oh, okay. So what I had mentioned is for a very serious system, have
Uh-huh.
two power supplies, two power supplies for the PLC. One is the main power supply, and then the second power supply is redundant power supply. But now this power supply is connected to a UPS system.
Okay.
And then on the side, power supply and the secondary power supply. And that way you're able to mitigate any eventuality of any power issues related.
Okay, thank you. I think my question is answered on power supplies.
Yeah.
I don't think there's any other question.
Okay.
Yeah, I can see people have left, and today's session was informative, and I would like to thank you so much for taking your time. Where I am attached at, they have like PLC system, and it's quite complex because everything is very automated. If it's reception of milk, it's done by a PLC. If it's cleaning, it's done by a PLC. If it's the mixing of components, if it's milk, making flavored milk, it's PLC that does it. So it's like everything is done by the PLC. And you find that sometimes these PLCs have issues, and we are
Yeah.
called upon to fix it as attaches. So this is a very good session, and I would just like to encourage anyone who's still on the call to keep on attending. Yeah. And once again, thank you, Jared. And
Yeah.
tomorrow tutakuwa we'll join the call. Yes.
All right. All right. So which company are you in?
Uh, Daima Dairies.
Okay. Okay. All right. All right. So, yeah. So, yeah, I just decided to give this a kickstart so that you guys can be able to understand what happens in the field. Yeah, because here we're not talking about microcontrollers. We're just talking about serious PLCs and serious processes. Yeah. So, your friend who is not attending, it's a free course, and once you have these basics, you can of course be able to do anything. And once I will give you access to now the softwares, And I have the real hardwares. If you want to do a real-time simulation on the hardware, you just do a remote connection and you're able to use the PLC here. And you can be able to control and see what's happening on the PLC.
Okay. I think that will be very useful for us. Yeah. Okay.
Okay. Thank you so
I
much.
think welcome. Okay, I think we can now end the meeting.
Okay, you have a nice. Yeah, you can actually end the meeting. So tomorrow, I've not seen guys. I think Nani was not in. Ben, many people that were yesterday weren't in. Today, I don't know what happened. Maybe you can just do a follow-up and just check, remind them. Yeah. How
Okay.
are the courses? Is it too intense?
Actually, no, it isn't. If you have like a background, or maybe if you've seen these things, I think it's a bit easier. But if you haven't, I would like try to tell the others just to probably research on how some few things, like how they look, just to get a basic view, an imagery on their mind of how it looks. So once you get that, I think it will be easier to actually understand. Yeah. But the course itself, how you're taking us through, it's very easy. I had a person who was teaching me and I didn't understand anything. I was I was a bit confused, but now that it's going slowly, I can understand some of the core concepts that you're talking about: normally close, normally open, and start or coil, start, stop, and all that. Yeah.
Yeah. Okay. Sure. Thank you. You're getting something. All right. Encourage your friends. It's a free session, and once we're done with these, yeah, I think we can organize with either IEEE and said we can come up with maybe even just giving people some recognition about certificate about the training and everything is something that we can do, of course. See what we can be able to gain from this so that people can at least have something. You did a 4 intensive course on PLC programming, just into basics to PLC program, at least to showcase something. Maybe just something can just organize within the IEEE and said, then we can see what we can do about that.
Okay. I'll inform Chris, and yeah, we'll try to organize with him.
All right,
Okay.
so that people who are here can be able to at least to appreciate. So thank you so much and have a lovely evening.
Thank you, you too.
Okay,
Thank
bye.
you.
Thank you.